Okay, so welcome back to another video. Today we have a little calculus problem for fun that we want to solve, and that is to find a function f of x. Of course, f can map from the reals to the reals, such that f of x is equal to the integral from 0 to x of f of t dt plus e to the power x. So sadly, this video intentionally was meant to solve this given problem in two ways. The first way being is what today's video is going to be, so hence it's going to be short. And the second way is to use some f of x that can be written in an infinite sum, plug that infinite sum back to the function to our given equation over here, solve all of that out and simplify it out to get the final answer that you'll see by the end of this video. So the obstacle I ran into, of course, was trying to find some f of x function infinite sum that satisfies this following. So there's the fun ruining that for me, but instead how about this? I'll let you guys I leave this as an exercise. See if you can find some f of x that is written as an infinite sum, such that if you plug that infinite sum back into the equation, you'll get the final answer simplified. So in this method, the way I'm going to solve, and I know it's the only one way, that's why if that was the case, then this video could have been a little longer than it should have. It's basically just we want to, for example, find some constant. Well, it's more of like a plugging in a trivial guess, the trivial checks. So in this case, like we say x is equal to 0, solve from there, and then find what our constant is. Then utilize that to help rewrite the function, all that. So eventually, this will lead into a something you will definitely see in a introduction course of ODEs. Then you just solve that ODE and then you just get the answer. So yes, basically this video is basically like an example of an ODE problem, but to that predecessor, it's just use a little bit of calculus, then working our way to there. So anyways, I don't have anything else to add, so we can just jump in. So if we do some trivial check, let's say if we let x equals 0, right? All right, so if we were to plug this in, then we would have that f of 0 is equal to the integral from from 0 to 0 of f of t dt. Then add this with e, and then plug 0 over here. All right. So what that would have to mean is that using with intervals of the integral, if it's under the same number, so that means you're not taking account to any area, so therefore no area is being calculated, and therefore it's just 0 for this term right here. Then add this with e to the power 0, which is 1, which is equal to 1, and therefore that shows that f of 0 is equal to 1. So we have formed ourselves a little initial condition to help continue things further from here. Next, what we can do now is let's actually take the derivative of both sides of the equation. So in this case, if I do f prime of x, then we take the derivative of our integral, but that's basically just using the fundamental theorem of calculus. The integral sign just cancels each other out, but you also plug x back into here, but also take the derivative of x, which is just 1, so you'll just get back, this is just f of x. And then the derivative of e to the x is just e to the x. So let's actually make ourselves a little easier. Let's actually do a little substitution. And in this case, we'll let y equals our f of x. If we have an f prime of x that's just taking the derivative of y, we can write that in a form of a Leibniz notation, the dy over dx notation. Set that equal to f prime of x. And then we can actually put in our pieces there. So now we have ourselves the following substitution. We would have dy over dx is equal to, so f of x in this case would be equal to y, and then add this with e to the power x. Then I can subtract y to both sides. Then we have dy dx subtract y is equal to e to the power x. And this is nice because I just said that this is something you'll see in an ODE class, and you'll notice this is actually in a form of a first order linear equation. So here, linear equations devise the following statement, or the formula here, where in conjunction with whatever correlates with y is your p of x function, and whatever with your function on the right, that's your q of x. So we can write and state that p of x is just equal to -1, then q of x is equal to e to the power x. Then what we need to do, if you learn in linear equations of the first order, is you have to multiply an integrating factor. We can define this as mu of x, and we say that that's just equal to e to the power the integral of the indefinite integral, what we don't need to do with the constants, of our p of x dx. In other words, substitute the -1 back in, so e, and then it's just a negative, so I'll put that outside, dx. That's just equal to e to the -x. So we can just plug this back to both sides of the equation. So here we have e to the -x, dy dx. Then subtract with y times e to the -x. Then multiply e to the power x with this. So this will just become 1. Then we could just you notice that we can actually write this in a form of a product rule, like going in reverse. And then we also want to take the integral of both sides. So here I can write this as the indefinite integral, the derivative of dx of y, and then y times e to the -x, then times dx. Set this equal to the integral of dx. Okay. Then if just by performing the left-hand side, we just get y equals, or y times e to the -x, then set this equal to x, and then add this with our constant that we're trying to solve. Now we can just divide e to the -x to both sides just to get the y function by itself, and it also makes sense to do this since we also said that we do a substitution by saying y is equal f of x. Now next it's just y, then divide by e to the -x. In other words, it's just the same thing as x times e to the power x, and then add this with c times e to the x. Then from here, we can also write this as, or in other words, I'll just say that we can write this as f of x equals x times e to the x plus c to the times e to the x. Notice that we just found the condition, we found our little initial condition saying f of 0 is equal to 1. So we could just plug that back in. So f of 0, set that equal to 1, and then I'll just put that equal to, so plug in 0, so this is 0, then e to the power 0, add this with c times e, and then to the power 0, then f of 0, or no, I shouldn't write it like that, I should write it as 1. 1 is equal to, so this will be 0, and then e to the 0 is 1, so that's c. So that's what we got. C is equal to 1, so we just plug that back into our f of x function, and just therefore pretty much we're done. We just found the function that f of x is equal to x times e to the x plus e to the x, or, and I guess if you want to go a little simpler and then just factor out the e to the x, it's just e to the x times x plus 1, like so. So there we have it. We found our f of x. Of course, it maps from the reals to the reals such that it satisfies the equation like so. So again, I couldn't find a infinite sum that would satisfy the equation behind me, but if you want to try it for yourself and see that if you can find some function in a form of an infinite sum, then plug this back in, see if from all this you get this answer like so. So yeah, that's pretty cool if you ask me.